Okay, good morning everyone. This work is done by the team from Xi'an Jiaotong University, but unlikely, all authors are unable to be here due to the visa problem, so I will be presenting this work on their behalf. I am Tianren Luo, and a PhD student at the Institute of Software in the Chinese Academy of Sciences, and I'm here to present this work, Mobile Task Automation, using vision-based UI understanding and LLM task planning. In this work, they propose a vision-based method for general mobile UI understanding with an LLM for task planning and automation. The codes are available on GitHub. In today's fast-paced digital age, smartphones are essential for managing tasks like email, online payment, and scheduling. However, for old people, disabled people, or those in distracting situations like driving, a smartphone use can less convenient. Repeat tasks, such as setting many calendar reminders or sending similar messages, are time-consuming and prone to errors. Previous solutions have adopted different methods to address task automation. For instance, Suglite employs a programming by demonstration approach, automating tasks through the recording and replay of user action sequences. Screen passing achieves automated understanding of interfaces by in-depth analyzing the relationships between elements. One's work represents an initial exploration into leveraging LLMs combined with mobile UI view hierarchy to promote automation. In this paper, we propose VisionTasker, a visual-based mobile task automation system that combines UI understanding with LLM task planning. VisionTasker can automatically do daily life tasks, such as setting reminders, sending messages, or checking bills. It observes your phone screen step by step, understands its content, and simulates human actions like clicks and inputs to do the task you need, acting like an invisible assistant helping you operate your phone. The core of VisionTasker lies in two key technologies: visual understanding and task planning. First, it uses advanced computer vision techniques to see your phone screen and understand elements like buttons and text. Then, it uses large language models to determine how to do tasks based on what it observes. The first phase of VisionTasker is UI understanding. Our method bypasses the view hierarchy and directly analyzes UI screenshots. We started by detecting interface elements such as buttons, sliders, and text boxes using YOLO. Afterward, OCR is applied to extract any text display on the screen. Next, these elements and text are grouped semantically based on visual layout principles. A CLIP model is then used to classify over 170 types of commonly used buttons. We detect UI boundaries and segment the interface into blocks. Active types are identified through HSV color analysis, and block captions are recognized from plain text at the top of each section. Finally, all recognition results are translated into structured natural language, which is used to generate prompts for LLM. After UI understanding, the challenge we face is how to translate the information into specific action steps. To address this, we refer to the chain of thought method. By using a planning step-by-step approach, we guide the large language model to plan the sequence of action gradually based on the screens. The prompt includes the task description, previous actions, and UI semantics from the current interface, allowing the LLM to determine the next action. Moreover, when the LLM faces challenges during planning, we enable the programming by demonstration method. This provides the LLM with extra context information through human demonstration or history data, helping it find the correct path to do the task. By these methods, VisionTasker can convert high-level task orders into a series of actions for automated control of mobile applications. Next, please watch a demonstration video. It will show you how VisionTasker does a practical task step-by-step going to Alipay to analyze annual spending. In evolution, we first focus on the accuracy of UI understanding. We used a dataset of 136 screenshots from 31 popular applications, covering different UI layouts from system applications to popular third-party apps. We evaluated the precision and recall of element detection, icon recognition accuracy, and the quality of answering screen-related questions, using learning bot based on the generated UI semantic descriptions. The results show that our approach significantly outperforms the methods based on view hierarchy and those directly using LLM such as GPT-4 in most aspects. Next, we evaluated the effectiveness of our method in task planning. We used 470 tasks across 4 public datasets, including Motif, Meta, UGIF, and AITW, to test the system's ability to predict the next action required to do a given task. The results showed that our natural language descriptions enabled LLMs to plan tasks effectively with higher accuracy in predicting the next step compared to other methods. In addition, we tested our method on the 147 real-world tasks automated on Android smartphones. These tasks had multiple types, including media playback, social interaction, and online shopping. The results showed that VisionTasker outperforms human in handling unfamiliar tasks and demonstrated significant improvements when integrated with the PBD method. We acknowledge challenges with certain user interfaces, like dynamic ads that can't be captured by screenshots. Moreover, the waiting time for page transitions is inflexible, and the system faces challenges in handling delay and token cost. We aim to adapt VisionTasker for desktop tasks with further training, explore advanced planning methods to enhance automation, and conduct broader testing and application studies. My presentation ends here. Thank you. The authors look forward to further discussion with their work with you. Next, another student will participate in the following Q&A session.
Okay, great job. And here's Alex. And I have a question about your data perspective. So in your slides, you show the example like the apps are in the live mode. And because we know right now a lot of people they are using their apps in the dark mode. Have you tried to test the system on the dark mode apps, the dark mode UIs? Do you find any difference? Yes, this is two questions. Sorry.
Okay. Firstly, the public data set, we use it, and we modify it by, there are some tiny mistakes in them, so we fix all of them, and then use them to test our method. And secondly, I'm not a writer, I'm not familiar with the dark box test. Sorry about that.
Okay, cool.
Yeah.
Mingyuan Zhong from the University of Washington. Very nice work. I want to ask a question about that I observed from some of the users. So as a sort of task automation agent, people will try to execute like more complex tasks, right? So, for example, order me grocery from Walmart and maybe add some meat, add some candies. How do you, like, does your system support these kind of complex tasks? And how do you make sure these tasks are executed according to the plan and like you remember everything?
Oh, yeah. So in this model, if the app has the function of the PBD, that is the programming by demonstration, then we can use this function to help our model to accomplish complex tasks. And
so you're saying you need a certain type of app support from the app developer?
Yeah, that's true.
Okay, thank you.
Hi, it's great work. Thank you for talking about. I just have a small questions about, like you mentioned, you use YOLO V8 for object detection in a very early stage, building in this UIST backend. I'm just wondering, like, for YOLO models, they're kind of heavy running on edge devices. Like, what do you think about this challenging in the future? Or
yeah, that's a good question. So in this method, some of the operations must be done in the computer, right? So in the future, the future work is to get all these functions on the smartphone. So that's more convenient. And currently, we have no method to do that.
Thank you.